Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you so much for coming. My name is Amy Draves, and I'm pleased to welcome Tony Hay to the Microsoft Research Visiting Speaker Series. Tony will discuss his book, The Computing Universe. He was inspired by the fascinating overview provided by Richard Fineman in his Fineman Lectures, and he details the history of technology and computers from the early days until now. Tony is a senior data science fellow at the University of Washington's eScience Institute, and he formerly was a corporate VP with us here in Microsoft Research. He has authored many research papers and has edited or co-authored several books, including The Quantum Universe and Einstein's Mirror. Please join me in giving him a very warm welcome.
Thanks very much, Amy. Hi, well, it's really great to be back, and it feels slightly strange to be back in Building 99 without my badge, but nonetheless, it's great to be back. I will tell you about why I wrote the book. It's meant to be about computer science, because we know I've read lots and lots of books, popular books on science, on physics, astronomy, genetics, biology, all these things. But the science that's changed the world the most in the last 50 years is undoubtedly computer science, computer engineering, or whatever you want to call it. And there are very few popular books about computer science. And in England, I have 3 kids, and they all did an exam at the age of 15, and it was on ICT, Information Communication Technologies. And it was the most boring subject they ever did. And that is really so sad, because it's the world that we live in now, young people can make a big difference and change the world, and that's what's evident from the history of computing. So it was because I wanted to try and see if I could interest even my kids and find computer science was relevant and exciting that I ended up writing this book. And so this is Jeanette, who you all know, Jeanette Wing. She had this notion of computational thinking. I realize I'm speaking to an audience of experts. This is normally not given to an audience of experts, so I'll skip some of the details. But the idea is that it's more than just knowing how to use a word processor or a spreadsheet. Obviously not fitting on the slide. And it's more than being able just to write in code, to write in Python or whatever. You have to have something to do, and making the computer do something is an algorithm. And that's really the heart of computer science for me, is algorithms and clever things, ways to do it. And this was Jeanette's vision, and it's a vision that's been taken up very much in the UK, where they're now going to teach computer science in the same way as they teach physics, chemistry, biology, and computer science as a science from all the way up school. And they're very much inspired by this vision of computational thinking. Computational thinking came about actually from one of the heroes of the early days of computing, Alan Turing. Here's a computer photograph of a computer image of him. And Turing machines were deliberately based on what a person would do, how you get a human computer to do a calculation. And you have a piece of tape, you can move back and forward, you can put marks on it and so on. And that's what the Turing machine was, and it gives the definition, the formal definition for computability, and it gives you a way of deciding whether this algorithm is the fastest or the shortest time, or uses more memory, or whatever. So you have a way of classifying algorithms, classifying what things are computable, and also what things are not computable. So algorithms have been known for a long time. The first one is probably Euclid's algorithm, which is to find the greatest common denominator. For example, 8 over 12, you can divide by 4, and that's the greatest common divisor. And there's an algorithm, a precise way, you give it a fraction, and you can go precisely and find the greatest common divisor. And that's the essence of an algorithm. Over here is a person from the 19th century, Charles Babbage, and he had this idea very much about what we would call a modern computer. They never actually built it because the engineering standards at the time he was trying to do it were not quite available to do it. But you can see, for example, in the Computer History Museum, a replica of his difference engine, which was completed after his death. It was completed very recently. And this, of course, is Ada Lovelace, who, with Babbage, figured out how to program things. But I like this quote, and it sort of typifies what computer science is. I was a physicist. If we had an algorithm which did it, yes, we'd like it to be as smart, but we didn't worry whether it was the smartest or the shortest or whatever. But what he says, whenever any result is sought by the aid of the analytical engine, that was his machine, the question will arise, by what course of calculation can these results be arrived at by the machine in the shortest time? So computer scientists worry about those sort of questions. And they're sort of typified by, just take one example, sorting algorithms. So this is sorting a list of names from Bob, Ted, Alice, Pat, Joe, Fred, May, and Eve. And you just go through this list, comparing this one, and if this is before this, you switch it, and so on. And this is like a bubble rising up. And it's called bubble sort for that reason. It's a very inefficient algorithm, because when you've done that, you have to go through and do it again and again and again. And this is an example of a much more efficient algorithm for sorting the same names. You do divide and conquer, and then you merge them again. And so these are the sort of things that computer scientists care about. They care about new algorithms, new ways of doing it, what's the most efficient, and so on, which requires least memory, and so on. So, and complexity and so on comes from the fact that we can base that on Turing's model of computation. So, I started off as a particle physicist, and these are a friend drew these. This is meant to be a quark inside a proton. There are 3 quarks. As you can see from the arrow, this is an up quark, that's an up quark, and that's a down quark, and that makes up a proton. But they never get out. So these are funny objects that they're inside the proton, and we all believe they exist, but you can't see one by itself. It's called the quark confinement problem, or in this case, Gell-Mann's quark prison, and that's what I was working on. But I ended up doing this, building parallel computers. This is the Cosmic Cube at Caltech, Geoffrey Fox and Chuck Seitz, and they built essentially an assembly of hundreds of microprocessors put together to make a very powerful computer. And this was the first message passing computer. Previous to that, you have big crays and so on. And I was reduced to doing this because a Cray vector supercomputer in the 1980s cost millions of dollars, and professors, as you know, don't have millions of dollars. So this is the sort of thing we ended up building. And of course, the difficulty, it's much cheaper, but the difficulty is if you have to plow a field, it's much easier to have the plow led by an ox than by 100 rabbits. And so programming the thing so it actually goes and all these things do what you want is the challenge there. Okay, so how did I switch? Well, I was on sabbatical at Caltech in 1981, and this is Gordon Moore. And the Gordon Moore professor of computing at Caltech was Carver Mead. He was the guy who figured out why Moore's law is true. Moore's law was here in 1965. There were 64 components on a chip, and he said, well, in 75, it looks like a straight line. I think there'll be 64,000 by 1975. And roughly speaking, with the aid of large amounts of investment from the semiconductor industry, they've managed to keep this Moore's law, the fact that the number of transistors on a chip doubles every 18 months or so, keep it going for 50 years. So I went to a seminar at Caltech given by Carver Mead, and it was like this. It was the weekly seminar for the faculty and students, and we were all waiting, and Carver Mead didn't turn up. And someone went and fetched him from his lab. He'd forgotten about it. And he came with his box of slides and gave a scintillating talk about Moore's law. And I remember in 81, he concluded there were no engineering obstacles to making everything smaller, faster, and cheaper for the next 20 years. And of course, he was wrong, because it's gone on for over 50 years altogether. So it became clear to me that that was really the future. And this, just to give you a quick thing, this was a key invention. This is Intel's memory chip, around a few thousand transistors on this chip in 1970. The big difficulty of the early machines was the building enough memory, all right? And we all know Bill Gates' famous quotation, 64K should be enough for anybody, all right? It's because memory was so expensive and so difficult, but this was the beginning of making memory cheap, and then this was the thing that changed the game. Intel were approached by a Japanese manufacturer who made a whole thing of calculators, and rather than make they wanted a range of chips for each calculator with different capabilities. But Ted Hoff and his colleagues at Intel said, well, why don't we make a chip that we can program? And then you can program it to do this, this, or this, and it's only one chip. And that was the beginning of the microprocessor. And I don't think Intel fully understood, the implications of that, because now we find those in cars, in refrigerators, in mobile phones, everywhere we find microprocessors. And so it was really the engine of the revolution. And this had a few thousand chips in 1971. This is an Intel Xeon, 2015, has 4 billion transistors. Now, that is remarkable. That challenge of computer science is actually, can you get 4 billion components working together doing something useful? It is really a remarkable achievement of computer science, managing the complexity to do that. And this is a slide from Gordon's original paper in 1965, long before there were PCs. Here he had notions, cosmetics, and handy home computers. So it was really an interesting paper. So after that, I went really enthused to solve my quark confinement problem on a parallel supercomputer using microprocessors. What I didn't know at the time was that my hero, Richard Feynman, he was famous for the Nobel Prize for Feynman diagrams. He also wrote a very famous series of lectures on physics, the Big Red Books, 3-volume lecture series on physics with Caltech. And he also was on the Challenger inquiry and did a famous demonstration live showing what the problem was, even though the commission he was on were trying to whitewash it. And he wouldn't have any of that. So he's a very good hero to have. And he was my hero. And what is not so well known, that he spent the last 5 years of his life lecturing on computing. And it's because his son went to Caltech. Feynman, as you know, when he gave a lecture, he was really entertaining and sparkling, and he used to take great pleasure in annoying philosophers, right? So he used to say, philosopher says it's essential for physics that the same conditions produce the same results. Well, I've got news for him, they don't. And all the philosophers used to walk out of his lecture, and he used to be enjoyed. But then his son went and did philosophy at MIT, which upset him. But then he changed to computing and worked for thinking machines, and Feynman was a consultant for thinking machines. Anyway, so this is Feynman's view of computer science, the limitations due to maths, limitations due to noise, to thermodynamics, to engineering, and also the limitations due to quantum mechanics. And in this, he sort of proposed a quantum computer, which, as we know, is being pursued by a number of 3-letter agencies based around DC, but also by companies such as Microsoft. And these lectures I wrote up at his request, and they're really aimed at a Caltech grad student. But they were really very insightful, and Feynman also, I discovered, gave a lecture at the Esalen Institute on Big Sur. Now that's a very sort of an alternative therapy thing, and you can just imagine the sort of audience who was listening to Feynman telling them how computers work. And so if you look at the video, that was one of the things that inspired me to try and make a popular version of this. And that's what this is an attempt to do. It's meant to be a popular book about computer science. It's meant to interest young people, if they still read books, that is. So it's got pictures and anecdotes and stories, and also shows how young people change the world. So let me now just take you a quick run through and show you where we've got to and what sort of applications we're going to be doing in the future. So what I like is Butler Lamson, who is a Microsoft Technical Fellow. He likes to classify the ages of computing in terms of the types of applications. So for the first 30 years, we were using them for computing, basically. We were doing it to design aircraft, to do galaxy formation, to do weather forecasting and things like that. by and large, in computation, spreadsheets as well. And then we got to connect them up together, and we've been learning how to do them with the internet, and we now have all sorts of applications, the search engines, we have web pages and so on, and social computing is the latest development in that. But since 2010, they've been engaging with people in intelligent ways, and that's what adding AI to all this computing and communication. So let me give you 2 examples of what's meant by embodiment, which is what he calls the third age. I think I prefer intelligent, but this is what Butler says. So to give 2 examples, I was shopping in England with my son Jonathan, and we got back from the supermarket, and there was only a tight parking space, and he was in his Volkswagen Touran, and he said, "Oh, what's this, Dad?" And he pressed a button, and the wheel turned by itself, and it did a perfect parallel park. Now that is something we would all like. Parallel parking is particularly challenging at times, and that's something we would welcome. But as you'll see from this talk, that along with the good things, sometimes come some bad things. So I was visiting a friend of mine, Horst, in Lawrence Berkeley lab, up on the hill in Berkeley, and he was telling me the story. He had to go to Livermore Laboratory to see one of his bosses, and he took a lab car to go there. When he got to Berkeley, his boss said, "I'm terribly sorry, Horst, but I'm going to have to report you for speeding." The car had reported him for speeding. He didn't know that, so that's slightly scary, but that's the sort of upside and downside of these applications that have intelligence. So let's quickly go through the first age, and it started really with these guys, John Mauchly and Presper Eckert, at the Moore School of Engineering in Philadelphia, and they built this machine. It was 8 feet tall, it was 80 feet long, weighed 30 tons, and had 17,000 vacuum tubes. And of course, all the early computer pioneers thought the major challenge was keeping this huge amount of hardware running. It's a complicated thing. But actually, all the work was done by these people. And these were the women programmers of the ENIAC, and you had to program it by connecting up the various components for a particular problem. And as we all know, the challenge in computers is really as much in the software as in the hardware. And so these people now finally have got some recognition for their work. But I would like to give, because I'm English, a little English diversion here. As I said, the early computers, the difficult thing was getting memory to store enough data and results and so on. Because of that, Maurice Wilkes was a professor at Cambridge in England, and he built what he called the EDSAC. It was in homage to the design document called the EDVAC, which was put out by Eckert, Mauchly, and von Neumann. It was the first fully operational stored program computer, where you could store the program and the data for the program, the calculations, in the memory. And the reason he could do it was because of this. This is mercury delay lines. The signal can go up and down here, and so you can delay the signal. And the reason he was able to build it before von Neumann, before Mauchly and Eckert were in a patent dispute with the university, typical problems with universities, and von Neumann was using a different technology. But he had an astrophysicist called Tommy Gould. He's the guy who figured out what pulsars are, rotating neutron stars. So he's famous in his own right. But during the war, he'd been working on radar, where you do a sweep with radar, and then you do another sweep, and you have to compare the two to see if anything's moved. So you have to delay things. And he'd built delay lines, mercury delay lines. And that was the reason why these guys were first to offer a computing service for a university. And that's what they really built. And this guy is the first computer science PhD, I guess, 1951. What did he do? Well, this is Maurice Wilkes. I can remember the exact instant when I realized that a large part of my life from then on was going to be finding mistakes in my own programs. And we all know that. But the idea was, what they invented was, if I figured out how to multiply 2 matrices and got some complicated machine code to do it, which works, it makes no sense for everybody else to do it. So you'd like somebody else to be able to use my code. So they invented the idea of software libraries, and then you had to go through the program, going through the program instructions, and you had to go from this point over here where the program for matrix multiplication is stored, do the multiplication, and then jump back. And that's called the Wheeler jump, and he invented how you do that. And David Wheeler and Wilkes wrote probably the first book on computer programming. Okay, enough. And then the 50s and 60s, we had IBM, where you took your cards and handed them to an operator who was the high priest, and you weren't allowed to touch the computer. The programs looked like that. Mine wasn't quite as big as that, but it was not good to drop your card deck on the floor and have to reorder them. But really, the exciting times came in the 70s. I would like to say about the miracle at Xerox PARC. Xerox had this Palo Alto Research Center, and they built what was called the Alto. It was the first recognizable personal computer in that it had a WYSIWYG word processor. Charles Simonyi was one of the people there, of course, who came to Microsoft. It also had Ethernet, you could connect it up, and they invented the laser printer, so you could actually go from here, print a document on the laser printer, and it also had a Windows interface with a mouse, icons, pull-down menus, and all that sort of stuff. And this is Chuck Thacker and Butler Lampson, and they're both now technical fellows at Microsoft Research, and they were the architects, hardware and software for the machine. There's a nice story about Lois Lampson, Butler's wife. She was the first person to have her thesis. Remember, they used to type theses, typewriters, and they used to have carbon copies, and you took them to the university and handed them in. And so she did that, took 2 copies, and she handed them in to the clerk, and the clerk said, well, which is the original to give to the library? And she said, oh, it's done by a laser printer, they're identical. And she said, no. And so they had a long argument, and in the end she said, that one. All right. Okay, so, and then we have, this of course is the famous picture of Bill and Paul at Lakewood, and that's the famous picture of Microsoft when it was in Albuquerque. I think there were 2 people missing at the time. And this was the Alto built on the Intel's new 8800 chip, and you had to program it with the switches. So having a basic compiler was a hell of a lot easier. And that's how it all started. But in the middle 70s, it was the hobbyists who made the progress. It wasn't the professional companies, computer companies, nor was it the academic computer scientists. It was a bunch of hobbyists. This is the Homebrew Computer Club. Now, at the time I was a physicist, this is at Stanford Linear Accelerator Center, and to my chagrin, I was actually at Stanford Linear Accelerator in 1975. It was a very exciting time. We just found a new quark, the charm quark, but I didn't know any of this. Interesting. Okay, so, and then of course, Steve Wozniak produced the Apple I. Steve Jobs realized that people wanted it packaged, and so that was the Apple II, and then the Mac, and so on. And the rest is history, as they say. The only application that they didn't have at Xerox PARC was, of course, the spreadsheet. And this is Don Bricklin. He was sitting bored in a lecture in the Harvard Business School, and had to do all these exercises where you change parameters, and realized it was a hell of a lot easier if you could do it on a computer. And so that was the thing. What I should say about the Xerox PARC effort, it never became a popular machine, but that was partly the time it was done, in the early 70s, when memory was very expensive. It used a huge amount of memory. But Chuck and Butler both understood Moore's law, and they understood it was very expensive then, but it would be very cheap later on, as indeed it was. And then this is the thing that sort of established Microsoft and established PCs in the business world. ControlAltdelete was invented by an engineer at IBM called David Bradley. There wasn't quite enough room to put a reset button on the board in a convenient way, so he chose these combination of keys. It would be difficult. And there's a nice conversation of him and Bill Gates. And Bill is complaining about ControlAltdelete being such a pain. And Bradley said, well, actually, you were the person who made everybody use it. And of course, this is another of the killer apps, if you like, for the consumer market computer games. This was PacMan. It was the first game that actually appealed to both sexes. Okay, second age of computing. This is my hero in computing, J.C.R. Licklider, professor of psychology at MIT. And he had this vision. concept of the intergalactic network, which he believed everybody could use computers anywhere and get data from anywhere in the world. This is Larry Roberts, the guy who built the ARPANET. He went to the ARPA and got this vision. His successor got the money, and then Larry Roberts built it. And this is a thing from their paper, these nodes connected by these message processors. And the idea was that everybody had these very expensive computers, and what you could do was connect them. And then, you know, someone at UCLA could use the computer at Utah. Now, this was the first ARPANET node. It's all on the West Coast. That was because all the guys at MIT, Harvard, and places, we don't want to share our computers with anybody. So they were not very keen on this, and they'd invented most of the stuff. And that's why these were the first in 1969. This was the ARPA network. And of course, very quickly, it became much bigger. 73, I remember logging on from UCL in London to Caltech to use a computer at Caltech in the 80s. And this is the killer app for that. Mae Tomlinson at BBN had the idea of using that. There was email on a computer locally, and he just put this so you could actually do it across the internet. Well, it was the ARPANET at the time. This is a representation of the internet, TCP/IP and all that. And of course, now we have billions of computers connected to the internet, and roughly more than 3 billion people in the world can actually log on to the internet, a third of the population. But it was this guy who made it usable. I gave him his first honorary degree when I was head of department in Southampton. Tim Berners-Lee. And there's an amusing story. I was watching the Olympics on NBC when they were in London, and they had a whole elaborate opening show, and at one point they homed down, they opened doors, and there was this guy hacking at the computer. And the NBC commentators in America had not been briefed. They didn't know who Tim Berners-Lee was. They do now, but it was interesting. They had no idea who he was and what he'd done. Anyway, so he was saying, "Welcome to the world." And this is the first photo of friends of his who had an amateur singing group at CERN. And of course, then these guys came along. 1978, I was using a browser called Alta Vista, and it was a good one. But these guys, being young, Sergey Brin and Larry Page, had the idea, Stanford grad students, they could do better. They wanted to look at the communication stuff. So their algorithm that they developed was very much like citations of academic papers in research. And so instead of counting how many times the words mentioned on the page to be most relevant, they wanted to see how many links pointed to it. And of course, the more links point to may be more relevant, but if it comes from sites where nobody cares, if it comes from a university professor or a Nobel Prize winner or industrialist like Bill Gates or whatever, then that site is more important, and they gave it more weight. And that was the PageRank algorithm. And they set up a network to do the search on Stanford campus. And then they tried to sell the algorithm. They went to Alta Vista, which was owned by Digital at the time, and they said no. And he went to Yahoo, and they said no. But one of the founders of Yahoo, David Filo, who was actually also a Stanford grad student, said, you know, why don't you try and set up your own company? Okay, they did. And this is a shot from the Microsoft Digital Crimes Unit, just a random shot, just to show there's bad sides as well. You'll see that most of Spain seems to be a botnet. So does Mexico. Brazil and USA don't do too well. Canada does quite well, but nobody lives there, of course. So anyway, all right, enough. Computers for embodiment. So let me show you. Here I want to go here.
What if your car could actually see what's ahead and respond right in the moment? A radar sensor and advanced cameras, including a new stereoscopic camera in the windshield, allow intelligent drive to recognize objects 360 degrees around the vehicle. Radar sensors give it foresight. Long, short, and multi-range radar scan the environment in front of the car, behind it, and out from the rear corners. The intelligence comes from insight. Advanced computing power interprets what it sees, determines the best response, and springs into action faster than humanly possible. The systems of intelligent drive can recognize a pedestrian entering your path, vehicles ahead slowing to a stop, and even cross traffic at a nearby intersection. The moment it does, it lets you know. As soon as you brake, even if it's too lightly, Intelligent Drive can increase it to the precise amount needed, even applying full braking power. And if you don't respond, it can initiate braking on its own, all to help reduce the chances or severity of an accident.
Okay, so that's Mercedes. There's an advert for Mercedes, and you've seen things like that. So I used to work with people like Mercedes and BMW in Europe on industrial projects in the 90s. And therefore, I've been slightly puzzled by, the Google driving cars, because they've had this technology for many years in these companies. But the difficulty is legislating and making sure you can drive it safely. What if it has an accident, who's responsible, and so on? Is it the programmer, is it the company, or whatever? So deploying it is interesting, and it'll be interesting to see where that goes. But clearly it can do some things really well, like self-parking and stuff like that. Okay, so how does that work? Well, how does it recognize a person from a car, from a building? Well, those are the sort of things that I learned about in my time in Microsoft Research. People like David Heckerman and Carl Cady, who taught me a little bit about machine learning. This is also, I do have a paper on neural networks. This is an artificial neural network. We have about 100 billion neurons or so in the brain, with trillions of synapse connections between them. Obviously, this is a very simplified version. Here we have 3 hidden layers: output layer, input layer, but we have lots of connections between them, and you can adjust the strengths. So, for example, you can train this to recognize a number plate. So you can train it to recognize E or 8, and you can adjust the strengths until the output identifies that it's an 8 or an E, and so on. And then you can have a camera that automatically reports you for speeding by recognizing things, a number plate on your car. So computer vision is one of the areas. Speech processing is another. And this is one of the earliest types of machine learning algorithms from very early on with von Neumann and McCulloch and people like that. But there's been great excitement recently with these deep neural networks with multiple layers there, where you can train it to recognize different features, and there's been great progress. And it's ironic, really, that a small child can recognize it's a cat, not a dog, in a photograph, and that's quite a hard thing for a computer to do. But we are making dramatic progress in these things with these deep neural networks. And so that's the sort of algorithm. Another algorithm is the one that we all know about, Connect. This is the 3D camera showing you 3-dimension. This is further away than this. And then you train it on lots of images. These are synthetically generated images of people, fat, short, young child, old child, and you want to recognize it's my hand, not the hand of the person next to me, or my arm may be obscured by me standing next to the person. And of course, you have to have good sound engineering. And that's, again, using a different machine learning algorithm. Decision trees, decision forests was how that was done by the Cambridge group and help from other Microsoft Research Labs with the Xbox team. And of course, now you put those two together, the computing and the communication, and you have the cloud. And that turns this sort of device into something really powerful. So unfortunately, this audience, I can't make my normal joke, you see. This is Cortana and Master Chief here. And so when I speak into my phone, I usually say, well, the audience will talk to Siri, because most of them do, but on this audience, you'll talk to Cortana as well. Right? And I say, Cortana, open the pod bay doors, and the signal goes up to the cloud where the processing is done. They understand what's said, they do the speech processing, they generate the answer, and the speech comes back to me in less than a second and says, I'm sorry, Tony, I can't do that. All right. So it changes these devices, and it changes the world. And that's really an exciting set of new possibilities for applications. And so I just list 2 here. This is a device you may recognize, which can actually, measure all sorts of things about you. You can, alert you to the fact that you have an appointment. It can know your diary. It can know you have to go buy flowers for your wife or your husband or whatever. And it can also send text to your doctor that he's having a heart attack and things like that. So lots of potential for these sort of devices in medical areas. And this is I can speak in my Skype in English and it comes out in Chinese to my colleague in China and vice versa. So these are the sort of applications you'll see. And then, you know, I've talked mainly about transportation, but healthcare is a big one, and there'll be lots of applications in these other areas. And that's really clearly where the battlefield is coming, and smart applications in all of these areas will come. But I would like to say, you know, you've seen the good things, but there's also bad things. So Ed Lazowska showed me this, which you might find interesting.
This is a regular new car. The masking tape is only there because we agreed to obscure its make and model.
We'll give them the illusion they control the car for now.
Kaufman has been working on this for 5 years with multiple research teams.
You want to hit the fluids?
Oh my gosh.
There we go.
There we go.
What's that? What's that? What's that?
That's the windshield wiper fluid.
No, wait. So this is something that a hacker hit.
That's right. A hacker. Like obviously, you didn't turn on the windshield wipers.
I did not.
Using a laptop, the hacker dialed the car's emergency communication system and transmitted a series of tones that flooded it with data. As the car's computer tried sorting it out, the hacker inserted an attack that reprogrammed the software, gaining total remote control.
Oh my God.
The horn.
They're doing that?
They're doing the horn.
They could control the gas, the acceleration. They could control the braking.
That's right.
And they could do this from anywhere in the world.
So just stop at the cones here.
She thinks she's going to be able to stop right at those cones. Let's make sure that she can't, and she's going to drive right through them.
All
We'll
right.
have complete control of that brake.
All right, there we go.
Oh, no, 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 no.
The brakes
I
didn't
cannot,
work,
oh
right?
my God. I can't operate the brakes at all. Oh my word. That is frightening. That is frightening.
That is frightening. You all know that Dick Cheney had the wireless in his pacemaker turned off. So, because there was a plot in one of the movies when they killed somebody by attacking the pacemaker. He felt he was under threat. Okay, so just to conclude with some light relief, those are the sort of applications, the intelligent applications that the computer scientists of tomorrow, Microsoft, Google, Facebook, and so on, will all be doing. And it really is an exciting time. You can have people starting companies and doing all sorts of things, and the cloud makes that easier. So that's what's really interesting. So I'd like to end on a sort of academic note, since I'm back in academia. I'd like to talk a little bit about real intelligence and artificial intelligence, weak or strong AI. This is from Russell and Norvig's recent book. The assertion that machines could act as if they were intelligent is called you're simulating intelligence, as opposed to the really thinking. And of course, all the movies we see are the ones we're really thinking, and that's called the strong AI hypothesis. And so you've all seen The Imitation Game, I hope. And if you want to find out the correct history, read my book, right? Because it's slightly perverted. It's a great movie, but the history's not quite right. But anyway, he had the idea of the Turing test. You had connections to computers or people in two rooms. Could you tell between a person or a computer? And that was the idea of the Turing test. Way back in the early days of computing, he thought of computers and artificial intelligence. This is in 1997, Garry Kasparov over here playing Deep Blue here. And of course, it's well known that Kasparov lost. Now, we would have said that to play chess requires intelligence. But of course, Deep Blue had large amounts of parallel processing power. It had special chess chips. It was primed with all the openings and all the finishes. And actually, it just beat Kasparov because it had so much computing power, it could go deeper and see all the possibilities. Kasparov could go fairly deep, and he could also see patterns and intuition. The computer had none of that. It just did, by brute force, it was able to beat Kasparov. So that's weak AI. And then, more impressively, in 2011, IBM Watson beat the two best players at this rather obscure game called Jeopardy. Right. Judith likes it. Yes, it is. So it's a curious game. So you have to teach the computer lots and lots of information. It has to know about Belgium, dinosaurs, notable women, you know, huge amount of all sorts of stuff. And also it asks the question in a funny way. It gives you the answer. So it could say Brussels, and then what you'd have to say is, what's the capital of Belgium? all right? And that's the way it does these things. And so it has to understand all that. And it actually beat these two champions at Jeopardy. But David Ferrucci, who was the IBM engineer in charge of the project, also had a screen that the audience could see, which had the top 5 guesses that Watson was going to come up with. He only gave the top one in public, but he showed the 5, and he said you could look inside Watson's brain. And if you did that, you would find on some things that Watson had absolutely no idea what the question was about. It was completely in left field, all right? And it really had no understanding of the question. It had completely misunderstood. So this is a philosopher at Berkeley called John Searle, and he's been one of the people who's attacked the idea of strong AI. And so this is his Chinese room. You put things in here, and you look in a book, and it says, if you get this, you put that out there. And actually what you're doing is answering questions in Chinese. His argument was that he doesn't understand Chinese. And, you know, it looks as if the room understands Chinese, but he doesn't. He's just a rote machine. And so what he said about Jeopardy and Watson was, Watson doesn't even know it was playing Jeopardy, let alone that it won. Okay. So, will we have R2-D2 coming in to rescue us? Or will it be Arnold with the Skynet? Or will you fall in love with your operating system? And of course, there's lots of other examples, Transcendence, Ex Machina. I recommend Ex Machina. It's a sort of Turing test if you haven't seen it. It's a very interesting thing. It's interesting that even Bill Gates and Elon Musk and Stephen Hawking and people have said this is really, you know, a really serious possibility for the world, and that we're, you know, could be the last thing we ever invent because the machines will take over. I think that's probably overblown, but the question is, are we going to go to the next singularity? This is Ray Kurzweil, the singularity is near. Computers will become more intelligent and design better computers without us. Or this is Feynman's example, what he told people at Esalen. His example was of a computer, it's a really dumb file clerk. What does a file clerk do? He goes to the filing cabinet, takes out a card, takes it over here, does what it says, adds the total to this, puts the card back, takes the next one out and does it. And that's actually the von Neumann principle for doing a computer. And in order to tell him to do that, you have to instruct him in excruciating detail how to do multiplications or adds and things like that. But the reason why it appears smart is because it goes so fast. The inside of a computer is as dumb as hell, but it goes like mad, is what Feynman says. And so in this position, you know, it's just a very smart, dumb machine, or are we going to get a singularity? Well, I think we'll be down here for a long time, in my view. But you never know. And just up the road at the Allen Brain Institute, human consciousness is just about the last surviving mystery. What makes, we have 4 billion transistors on an Intel Xeon. We only have 100 billion or so neurons. Why are we self-aware and conscious and so on, thinking? What makes these simple little neurons actually give us awareness? That's a really exciting problem, but it could be a very long way off before we discover how to do it. Thank you very much for listening. So I finished more or less on time, Amy. People are free to leave, but I'm happy to answer questions until I get stopped by Amy. Yes?
You suggest reading your book to figure out the imitation game. Meaning, no disrespect, why shouldn't you read Alan Turing's paper?
I didn't say to figure out the imitation game, to get the history correct. Alan Turing's paper tells you about the imitation game, doesn't tell you about history, Russian spies and all this sort of stuff. Or who actually built the bomb, and the fact that the first prototype was done by Poles with assistance from the French. That's the sort of thing you'll get from the book. Alan Turing is Alan Turing. Yes?
You mentioned Richard Feynman. I have to ask you if you have a good story about him.
I have a good story about Richard Feynman. Thank you for asking. So Feynman, he was at the Manhattan Project during the war, the atom bomb, and afterwards he went to Cornell, and he thought it would be a nuclear disaster, and it took a long time for him to get back into working normally, and he had these ways of visualizing things. And he went to a famous conference at Pocono in New York with all the greats. It had, you know, Oppenheimer, it had Pauli, it had Teller, all these famous people from theoretical physics there. And they were trying to understand how to do calculations in quantum electrodynamics, right? So the things that explain light and everything else. It's called relativistic quantum electrodynamics. And the trouble is, you had all these things that suddenly did a calculation, became infinite, and people couldn't make sense of it. And so there were two papers there, one by him and one by Julian Schwinger from Harvard. And Schwinger gave a very elegant mathematical presentation. He was really powerful at maths. And Fineman waved his hands a bit, and he talked about electrons and positrons are anti-electrons. And he talked about treating positrons as negative energy electrons going backwards in time. So you can see why his audience might have a little problem with things like that. And so he came away enormously depressed. But a few weeks later, he was at an American Physical Society conference in New York, and there was a presentation by Professor Slotnick was giving a talk, and it was about the equivalence of two particular types of couplings of different particles to pions. And he concluded that they were different. And after his talk, the great Professor Oppenheimer stood up and said, Professor Slotnick, thank you for your talk. I'm afraid, however, I must tell you your calculations must be wrong because they violate Case's theorem. And Slotnick said, I'm terribly sorry, Professor Oppenheimer. I've never heard of Case's theorem. Oppenheimer said, don't worry, Professor Slotnick. You can remedy your ignorance tomorrow by listening to Professor Case present his results. So Slotnick, you can imagine, crawled off the stage and was not a happy bunny. Feynman couldn't sleep that night, and so he thought he'd do the calculations that Slotnick did using his methods. And so he did them, and he found Slotnick the next morning, and he said, Slotnick, old chap, why don't we compare notes? Slotnick said, what do you mean compare notes? He said, well, I did your calculations overnight. He said, what do you mean overnight? It took me 6 months. He said, I've got these methods, see? Right. Anyway, why don't we just look? And so they looked, and he said, Slotnick said, what's Q squared? Feynman said, oh, Q squared, it's just the scattering angle, you know? He said, but it took me 6 months to do Q squared equals 0. Feynman said, no problem, just put Q squared equals 0 in my formula and we can compare. So they did, and Feynman agreed with Slotnick. And then Case got up to give a talk and gave his talk about Case's theorem, showed that they were identical to all orders. After his talk, everybody applauded. And the back of the lecture there, yes, Professor Feynman, I calculated Slotnick's calculations last night, and I agree with Slotnick, so your theorem must be wrong. And then he sat down. That was when he knew he had something and he was going to win the Nobel Prize. So. Lots of funny stories about Feynman. I knew him when he was happily married, his third wife, an English librarian like mine, he had won his Nobel Prize. So he was very relaxed. He used to have lunch with the postdocs and grad students most days. So it was kind of fun.
So we have an online question, which is, do you think the connectome project will be able to successfully and fully map the brain whilst exposing the secret sauce of consciousness?
So do I think the connectome project... Okay, so funnily enough, when I was at Microsoft Research, I funded the connectome project at Harvard for 4 years. And I didn't think I got anything out of it. We could automate what it is. It's cutting through slices of a rat's brain to try and find the connections between the neurons and the synapses. And it sounds great. You're finding the wiring diagram of the brain, right? So everybody wants to know that. I came to the conclusion, and so what we were providing was technology that could help you automate that process in looking at this slice and finding the connections and stuff. And that was a valid thing for us to collaborate with them for. And that was okay. But I found it was rather as illuminating as, imagine a tangle of spaghetti cutting through a bowl of spaghetti. You really don't find very much. And actually, you need to know, it's a dead brain by that point. It's a narrow slice of a brain. You need to know what signals, what's happening, what these neurons do. So I think by itself, it doesn't. Maybe with an MRI and you know, it may be that Paul Allen Brain Institute, there will be progress, but I think it's a long way to go. But I did fund Connectome. Judith.
Yes, can I just switch now back to youth, Tony?
To who?
Youth, young people.
Youth, young people, yes.
So I'm sure you've been speaking around the world on your book and so on, and maybe you've spoken to young people. What do you think they're going to do with computing now that we're into this third generation, and that maybe the syllabus has changed in the UK and so on?
Well, first of all, I think there is really opportunity for them to go do things, but only if they're sufficiently educated and they understand that these are the skills they need to learn. That's one thing, and not everybody can do that. My real worry, I'm reading a book by Martin Ford. It's called The Rise of the Robots, Technology and the Threat of a Jobless Future. Because these things are really smart, right? You're making really great stuff. They will take out lots and lots of jobs that we currently think as needing intelligence. And it's not obvious. Every previous thing, you know, the agricultural revolution, everybody moved from the fields, but then we had factories in the cities and so on. We replaced them. It's not obvious this time, is what the book says, that we're going to replace those jobs. So I think it's protection to some extent, but I think there are opportunities, especially in the Internet of Things, of doing interesting things, and that doesn't cost a lot. And I tried to show young people, Tim Berners-Lee and Sergey and Larry, for example, all very young, and they did these things and made a difference in the world. And I think that's one of the things they can do. But I think it's to some extent self-protection, and working in IT and on computing technologies is a very wise thing to do, in my view. The book also has terrible examples, Martin Ford's book, of sushi house with no people there, because they have a machine to make sushi, and they have a way, the color of your plates, that it's automatic. You put them in the bin, and they send you a bill, and it comes to your table. There isn't even a manager on site. And then apparently there's a new machine coming out which can make gourmet hamburgers. So you don't need someone to make that. Anyway, so there's all sorts of technology that are threatening jobs. And I think, you know, that's the message I would get across. So it may be different this time, because of you guys.
Probably a silly question being a non-computer engineer, but I was curious about Moore's law, because, you know, when you say this is how it's going to be, and then you have thousands of people working on that project, do you think that Moore's law drove the capability, because people are like, okay, we can do this every 18 months?
Moore's law was an observation made in 1965 from about 4 points, yes. And of course, it's actually been kept true by the semiconductor industry. I think Gordon Moore once said, it's becoming exponentially expensive to keep Moore's law true. Right? And they've done really hugely innovation. They have this semiconductor roadmap, which maps out the technologies. But actually, I do think we're getting to the end of Moore's law, because I'm a physicist originally, and now we're getting down to atomic dimensions. And at the atomic dimension, things don't behave like the sort of billiard balls that we like to visualize. And therefore, I think Moore's law is coming to an end. There's already a slowdown, and actually what replaces it is extremely interesting. Is the industry going to be like airlines? You know, we cross the Atlantic, or at least I do, at about 600 miles an hour. It doesn't go faster. It hasn't gone faster for the last 30 years. Maybe we'll reach an asymptote, and then maybe you don't have to throw away your phone every 2 years. You know, it changes all sorts of things. So I think there could be some profound changes coming from the end of Moore's law, but there will be new things to replace it, and that's why the stuff here on FPGAs, for example, is an interesting thing. And we have GPUs. Maybe we'll have sort of graphical programming units, neural programming units. That's what IBM are talking about in Watson and stuff like that. So maybe different types of specialities. And I think there's plenty of room for innovation. But Moore's law, as it stands, will come to an end. But it's been a huge effort by the semiconductor industry to make it so. And it's truly driven everything. Yes.
I'm curious, you haven't mentioned the cloud as a
I did mention the cloud. I had a picture of the cloud. And don't forget, I talked to the cloud.
I mean, the thought that the cloud is now becoming ubiquitous as a utility like running water or electricity or any other sort of basic service.
You wouldn't think so if you went to Greenwater, Washington, on the way to Rainier. You can't even get a cell phone signal.
That's an RF issue.
That's a geography.
That's another branch of engineering.
Anyway, no, the cloud I think is important. I mean, one of the projects we did in Microsoft Research was called Greek Fire. There were these fires on the Greek island, on Greek mainland, which nearly reached Athens, which burnt 3,000 buildings down and killed 300 people or something like that. And so if it happened on an island, it could sort of wipe out the whole island. So what they did with the Greek Microsoft employees plus some people from Microsoft Research, with the Greek universities, they developed an early warning system which took data from satellite data, took real weather forecasting data, it had topography of the island, it had population, the roads, it knew where the fire trucks were and things like that. And if a fire started here, this was the most likely place. Where would it spread? Because of the wind direction, you could do all those things. Now, there's no computing for a supercomputer on an island, so that really did depend on having the cloud to do your computing. And those are the sort of applications that are made possible by the cloud. So I think the cloud's great. And I used to do startups with my staff in university. And, instead of them having to get large amounts of sort of angel funding to buy equipment, you can just start immediately. And it just makes a big difference. So I think the cloud is really important for all sorts of innovation. And I didn't talk about the other killer application, which is social networking, which also things like Facebook and Twitter and Flickr, all these things use cloud, right? So those are clearly going to be important. So I'm sorry if I didn't mention it sufficiently. I think it's important. Though everybody now has clouds. Thank you very much, Amy. Thank you very much.